Merry Christmas and a Happy New Year to subscribers, both old and new. There's been a little flurry of new subscribers recently. Typically I only get one new subscriber a month, but in the last 2 weeks there's been 8 or 9. So I don't know what that's about, but I'm glad you've decided to subscribe, and I hope you decide that it's a worthwhile thing to have done, both old and new. So I was planning my next video to be to do with power electrics, but there's a few things that I need to get done first. I can't do that, and I thought, well, I better put out something before any new subscribers and old ones lose interest. So that's what this video is about. Now, you may be wondering what this thing is. Well, it's actually a red herring, because this video has nothing to do with that. This video is about these things, which I recently received from AliExpress. They are Minimum System ATmega32 development boards, if you like. They've got a zip socket, and you can put an ATmega32 into them, plus a bunch of other chips, as it turns out, but I was interested in ATmega32, which is how I found these. So first, a bit of background. Back in the bad old days, when the only way to do things was the hard way, I used to make things like this, which have a processor, RAM, ROM and I/O, all as separate chips, and needed a fairly elaborate PCB to join it all together. But then along came microcontrollers, and specifically the AVRs from ATmega. And I started doing projects like this, with typically using ATmega 8s, because they got a reasonable amount of I/O on them, and of course these things have the CPU and the RAM and the ROM and the I/O all in one chip, so fantastic. And I've made homemade boards like these things, and that, another Mega 8 there. And yeah, that's fine, but I had to make my own PCBs all the time and muck around programming them, and I was only using assembler. And then I discovered Arduinos, and I could do things like this. There's a Nano on a homemade board, but the board's got a lot simpler because the little module there has difficult stuff taken care of, especially the SMD soldering. Plus, of course, you could use a high-level language, even though it's that disgusting thing called C. It made programming it easier. Especially what was really good about Arduino was the libraries for all sorts of devices. That's what I really went to it for, not because I wanted a high-level language. I'm happy with assembler, but the libraries were good. So I started doing a lot with Arduinos. Now, originally the Pro Mini, which is a nice little unit, very small. Both the Mini and the Nano are easily embedded into other projects. That's what I found attractive about them. This one, the Pro Mini, is fine for if you don't need any serial communications when your project's running. If you do, then the Nano's the go, because it's got the USB interface built in. For these things, and the Pro Mini, you have to have something like that to connect to it and to program it, and then also to act as comms. But Nano has got that built in, so it's sort of like this and this together. So they're great for embedding things, and like this one's got the ATmega 8, I'm not sure off the top of my head, but it's got maybe 16 I/Os on it, maybe 20. Same with the Pro Mini and the Nano, they've both got about 20 I/Os, and none of them are a full 8-bit wide I/O port. They're 3 of 6 bits. And there was the classic Uno, but that's very clunky. It's much bigger than these guys, and it's got these clunky big USB jacks and power jacks. But you could stick in all sorts of shields to do different things. But for embedded projects, you wouldn't use that. I wanted something more like these guys for embedded projects. And if you want lots of I/Os, well, then there's the Mega 2560. That's got about 70 I/Os, but again, big, clunky, expensive. Neither of these are breadboard friendly, whereas these guys are. You can stick them in in a breadboard like that, and also because they've got sockets rather than pins, they're not so easily put into an embedded system. You have to make it, you have to do it as a shield, and still too big. And so they're okay for experimenting and developing, but when it comes to embedding, you want things like these guys, and you can do that even for 2560s. Here's a project that uses this little module, which is a 2560, just a sort of cut down version of that. It's just basically the processor and crystal and the ports you need to program it via that. But again, it's expensive too. You know, that's probably about 17-20 bucks a pop. Again, double row connectors, which are not very good for, well, no good for breadboards, and they're no good for homemade PCBs. I find I have a lot of trouble getting wires between those pins on homemade PCBs, so I avoid them wherever possible. This thing there's about 70 of these made, but hand soldered, so I use things like that to not have to solder all this stuff, but of course in production you would put all that stuff on the baseboard and do away with these modules. So all in all, none of these were satisfactory for a project I had. Actually, I had a couple of projects in mind that would need more IOs than these guys, about 30 to 40 IOs, and these things were overkill for that. And I knew that I had some ATmega32s lying around, got a bunch of them there, and I thought, well, I could just do with those what I've done with the Mega 8s, just build them into a board, into the base unit without any modules, and all you have to do is add a crystal, 2 capacitors, and a programming header, and away you go. And you get 32 bits of I/O. The beauty of the Mega 8s are you've got 4 ports of a full 8-bit width, and they're nicely laid out on either side of the chip. The only fly in the ointment is PD7 is actually this pin here, but these boards bring it across to there, so you've got PD 0 through 7 there, PA 0 through 7 there, PB 0 through 7 there, and PC 0 through 7 there. PC works the opposite way, 0's down here, 7's up there. All the others it's 0 through to 7 going downwards. So knowing that I was interested in ATmega32s, I saw some of these online, and I thought, oh yeah, I'll get one of those. As it turns out, I must have chucked a couple in my shopping cart and didn't remove one, and ended up getting these 2. And that doesn't bother me because they're only about 6 or 7 bucks delivered, including this. You probably couldn't get a zip socket for that money, but so 2 of them I'm happy to have. Now, what's this? This is called a USBASP, and it provides the SPI programming interface that you can use to program these chips. That's what these pins on these projects are. And there, and here I'm using a Nano as the programmer to program this, so I can update this and set fuses and everything. All the stuff you can't do through serial comms and a bootloader, you can do everything this way. So you can use an Arduino for that, or you can use one of these. And these use the older format 10-pin connectors, whereas all these boards have, well, maybe that one doesn't. Okay, the Pro Mini doesn't, but the Mega has that 6-pin header there. The Uno has a 6-pin header there, and the Nano has provision to put in a 6-pin header. So you can program all those 3 using one of these, except that's 10-pin and these are 6-pin, and you can get these little adapters so I can plug that into there and stick that under that. Not sure if that's the right way around, and then program this thing without having to use serial comms, and you can do things like load bootloaders into it. No, sorry, that's for programming this chip, which is the USB interface. You've got to put it there, and again I don't know if it's the right way around. That's for programming the 2560. Yeah, so handy little gadgets, and almost free when you get them this way. In fact, you can get these things for maybe $2 or $3 delivered. These are Australian dollars, which are like 74.5 cents US. So let's have a closer look at the features of these things and then go on to actually try and use them. Right, so they both come with they don't come with any ATmega chips, you've got to provide that yourself. They both came with the USBASP device, like that. Oh, crystal fell out. These USBASPs, one has the pins going up, one has them coming out to the side, and one has parts on the bottom as well, but they seem to be pretty much equivalent. I've used them both and they both work with the experimenting I've done. These two gizmos, this one, they're about the same price, but this one's just a single-sided board, this one's a double-sided, and some obvious differences. The socket is on opposite way around, so if I put them there so that pin one's up here, then these are at the opposite ends. Doesn't really matter. And you've got your port A, B, C, D, again with port C working backwards, so 0 to 7 on these, but the other three it's 0 to 7 going down. They have a little crystals, that's where this fell out, so you can set the clock frequency by changing the crystal. They've got a power switch. On this one, when it's connected, when it's getting its power via that cable, on this one that power switch actually turns off the power LED. On this one, it doesn't turn off the power LED, whether it's on or off. I think that's only for this DC jack. And I don't know if you can get, I don't know if there's a standard for pin and hole size there for specifically for 5 volts, but these run straight to the 5 volt supply on the chip. So I don't like that, because I think a lot of people might try and stick 9 volts in there, because I think that's the more usual voltage. So, but frankly you don't need it, you can power it from here. Quality, well, you can see this one, the crystal's at a bit of an angle, and a couple of the resistors on here aren't fully seated. This one being single-sided has all through-hole parts for the LED and capacitors and resistors. This one has SMDs. Found a circuit that these things seem to match up with. I'll look at that in a minute. But yeah, they're identical, pretty much identical. This one also came with foots, so that's nice. Yeah, that probably looks better quality, but they both seem to work. They've got a little capacitor across the analog voltage reference pin. The crystal has the 2 capacitors that you always need built in there. So you've got your 4 8-bit ports, and then here you've got ground and VCC and ground for connecting things like testing LEDs. Connect that to ground, put that on a pin and see if you can make the pin oscillate. Yeah, handy little thing to make actually, these. Just a couple of DuPont wires going to a LED with an internal current limiting resistor. I think I used 270 or 330 ohms. So I've got a couple of those, which I found quite useful for experimenting with these things. So yeah, basically the same things. Now, programming them, right, when you buy an ATmega32, they're blank, they're virgin, there's no bootloaders or anything in there. So you've got to program that yourself, and that's why these are needed, because through the SPI interface you can actually burn the bootloader. Your normal serial port for there and there are only good if you've got a bootloader burned into your chip. But the advantage is that you can use it directly out of the Arduino IDE, provided that also knows about the board and chip you're using, which is the problem with these things. The Arduino IDE knows about nanos and pro minis and Arduinos and Mega 2560s, but it doesn't straight out of the box understand these boards and these chips fitted to them. So I went through a fair bit of buggerizing around to finally get these Arduino IDE talking to that, and so part of the video is to remind myself of how I did it and pass it on to whoever else might be interested. Now, I knew that trying to make Arduino IDE talk to these things would get messy, all sorts of geek nonsense involved that I wasn't looking forward to at all. So at first I thought I'll just try to work minimum stuff, just using my assembler IDE, which is a bit more low level, and it already knew how to talk to AVRDude, which is the software that seems to be used everywhere to talk to programming interfaces for microcontrollers. It can talk to these USBASPs, and it can talk to serial comms on these things. So I knew I'd only have to do minimum mucking around with software to tell my IDE to tell AVRDude to use this thing. The assembler IDE also already knew about ATmega, so that got rid of some problems straight away. And as it turns out, I've done a good job on that, because I only had to add one line in the configuration file, add another AVRDude programming option, which specified USB ASP as the interface, and straight away I was able to download something into this and it worked. Of course there's a billion other bugs that I thought I'd fix while I was there, but the essence of getting stuff into the chip, I only had to add one line of code, one line of the configuration file, which is not how it turned out to be for Arduino. Well, it is ultimately, but not along the way. Alright, so we'll take this and a Virgin ATmega32 and go through the process of what I did to get these things going. And then the last thing to do is add a interface for one of these, so I can program it via the serial port instead of always having to use USB ASP. To do that, which is pretty straightforward, it's just connecting power, ground and transmit and receive, but you do have to add one other thing, and that's a capacitor from the DTR signal on this to the reset pin on the microcontroller, because the AVRDude and Arduino IDE pulse that pin to do a reset on this chip. Otherwise you have to, in the old days, you have to sit around mucking around holding reset, pressing download on your PC and getting the timing right. Well, now you just press download on your PC, and via that capacitor and the pulse from this thing, the reset's taken care of. So now that I've shown you this, I can go ahead and wire on my capacitor and other wires to go to this thing. So we'll do that towards the end and see if we can talk straight from Arduino IDE via serial comms to this without having to use the SPI programmer. Okay, let's have a look at some data sheets. So let's have a quick look at some pinouts for these common Arduino devices. This is the Uno. It's got three ports. Two of them have 6 bits and one of them has the full 8 bits. But that 8-bit one, port D, PDs 0 and PD1 are used also for transmit and receive. So if you're doing serial comms, you can't use those 2 bits. So it's effectively 18 bits, 3 lots of 6. Pro Mini is much the same. Again, PD 0 and 1 are transmit and receive. So you've only got 16 I/O bits. There's these 2 other bits inboard of the main headers, but you've got to put in special wiring to get to those, so probably wouldn't use them unless you were desperate. Then the Nano, again, TXD and RXD use PD0 and PD1, and if you're using a Nano, it's probably because you're using comms, so you don't have PD0 and PD1 available. So once again, only 18 bits. The ATmega32 got I/O coming out of its ears, but as discussed earlier, impractical to use for an embedded system and for homemade circuit boards. And also these ports are all over the place. Like some of them are 8 contiguous bits like there, but there's a couple of bits here, a couple of bits up there, and one up there, and one up there. It's a bit of a dog's breakfast in places. And now the ATmega32. Now this is nice. It's a dip package, so it's 0.1 inch spacing, easy to use for breadboards and for homemade PCBs. And the ports are nicely laid out. You've got all 8 bits, PA0 to 7, PB0 to 7, PD 0 to 6. PD7's over here, but it's easy to just drag a wire across. And on those boards, that's what they've done. And PC0 to 7, which goes the other way. So full 8 bits, 4 of them, and nicely placed around the chip. Now, but still, it suffers from the same problem. PD0 and PD1 are transmit and receive, so if you're doing comms, instead of 32 bits, you've only got 30, which is still better than 18 or 16. The ATmega32 is not the only one of these DIP40 chips that can be put into these modules. Mega32 is 32K of flash, but you can put in others, and there's even this one, which is 4 times the size at 128 KB, and 8 times as much RAM and 8 times as much EEPROM. So, and I've seen those for only $7. And I've also got some 8535s and Mega 16s lying around. So all of those can be put into that same socket because they've got the same pin out. Now there's the blue module. We've discussed pretty much everything that's on there. Here's the 2 sellers that I bought mine from, World Chips and TX Hang on AliExpress. And for both items it was $3.30 plus 3 shipping and $4 plus $2.70 shipping, so pretty cheap, less than $7. This appears to be the schematic for these things. It's as close as I could find. It seems to match up. You've got your processor, of course, and the 4 ports here come out to these headers, port A, B, C, D. You've got the socket for the crystal with the 2 capacitors, reset capacitor and resistor, and a button to reset whenever you want, but the capacitor and resistor do an automatic reset when you power on. Here's the convenience headers, that 8-pin header with VCC and ground. This up here is the DC input jack. That's the switch, the power switch, and there's the power LED. And the blue one features this extra LED which goes to PA0, that port bit there. So if you're doing a blink sketch, you'd use that. I think normal Arduinos use PB5 for the onboard LED. Well, PA0 on these ATmega32s. Here's the ISP connector that goes to the USB ASP, and you can see 2 pins are ground. They've forgotten to put VCC on pin 2. There's your 5 volts, or 3.3, and these chips, some models anyway, can work down to 1.8 volts, so you can certainly run them at 3.3. Now some pinouts for these connectors show pins 4 and 6 also connected to ground, and some show them connected to transmit and receive. So, but that is what these boards appear to be. As far as I can tell, there's no connections to pins 4 and 6 on these. So there's the 10-pin connector. This one shows all 4 grounds connected on there. Some have TXD and RXD there, but these ones seem to have no connection. I haven't looked at pin 3, so on this one they ground it. There it's no connection. And here's recovery clock. I'm not 100% sure on that. I believe it's in case you've bricked or painted yourself into a corner with the fuse bits and you haven't got an external oscillator. So you can use a clock signal coming in here. I don't know if the USB ASP provides it. And there's the 6-pin newer version, and that's the adapter I showed you before to connect between one or the other. There's another view of the adapter showing the pin names and connections. And this is the ATmega 8, which I used on those very old boards, the homemade ones. And I always used to wonder why they used the 6 and 10 pin type connectors for ISP programming, because all the pins are nicely laid out in a row So a single inline connector would do it, and certainly that's easier for homemade boards and for breadboarding, etc. The only pin that's not there is reset. You have to bring a wire around for that. And VCC, well, you'd typically be connecting VCC for the digital side of the chip to the VCC for the analog, and so it would be available in this group as well. The Mega32, all these 40 pin jobs, all those chips are even neater. You've got all 6 pins that you need for ISP right there in a group. The only difference here is that reset and VCC are swapped compared to this here. So when I make boards for this chip using a single inline connector like that, I'll have to have a different cable to allow for that swapping of reset and VCC, but no big deal. Now this appears to be the schematic for the USBASP programming gizmo. It uses an ATmega 8. There's the connector through to the device being programmed, and it seems similar there, 2 grounds, but this shows transmit and receive connected, and they're shown here on the processor as well. Nothing connected to pin 3. So this doesn't do the recovery clock thing. It's got 3 jumpers. One of them is to select whether your device being connected is running off 5 volts from the USB connector over here, or whether it first goes through this 3.3 volt regulator and supplies 3.3 volts to your target device. This jumper is something to do with programming the firmware in there, which may look at later. And this is something to do with devices that have a slow clock. I'm not sure about that, but I haven't had to worry about those. There's a bunch of ways of programming these AVRs. I've only been talking about the SPI interface through an ISP connection, which uses the USB ASP, or as I showed earlier, an Arduino can be programmed with the Arduino ISP sketch, and it will do the same thing. They're equivalent, except that this one is programmed via serial comms, and this one's programmed via some USB protocol. And then there's bootloaders, which is always programmed via serial comms. JTAG, and there's a bunch of others. Not concerned with those at all, but there's a good tutorial on all the ways that you can program AVRs on AVR Freaks, so it might be worth having a look. So that's enough on the pinouts and theory. Now this video is getting a bit long, and there's quite a bit to go. Yes, this video has gone off a bit long, so I'll split it into 2 parts because I want to get something out, and I'll try and get part 2 done in the next few days, where we'll actually go through programming of this thing via that, and then hopefully via this, using a bootloader that we burn into there, and the trials and tribulations of getting the Arduino IDE to understand these boards and these chips. But that's part 2. So I hope you've found what you've seen in this video informative, and we'll be interested in watching the second half, so that'll be just in the next few days. In the meanwhile, I'll catch you later.